Hi, it's Bruce, and welcome again to my Rocky Mountain lab. And we're going to take a look at this Gertsch RT60 ratio transformer. These ratio transformers are voltage dividers for AC. Very similar to a Kelvin-Varley in the way that they function with the voltage. Kelvin-Varley will break down the voltage, DC voltage, into decades, and they're very precise. And in a correlating way, this RT60, it breaks down AC voltages into decades, and it's very precise. It's made out of tapped transformers. You've got, I think, 10 taps on each one of them. And they're very precisely made, and because of the way they're made and because of what they are, they're very rugged. They last for a very long period of time, and they're good over a frequency range of like 10 to 10,000 hertz. We're going to give this one a quick walkthrough using a 10 volt AC reference from this Fluke 510A. It's 1,000 hertz signal at 10 volts, and we're putting that on the input here, and then on the output we're coming back to my Hewlett-Packard 34401A. Right now, for that 10 volt input, we're getting 9.39s and an 8 on the output. Now I'm going to dial down on the highest decade, going to an 8. We've got 8 and 4 nines. And what we see is 8, 3 nines, and a 0.1 or 2. Looks like a 1. Let's go to a 7 and 4 nines. 7.9987. 6 and 4 nines, 6.998585. 5 and 4 nines, 5.9983. 4 and 4 nines, we've got 4.9987. Yeah. 3 and 4 nines, 3.9992. 2 and 4 nines, we've got 2.9998. 1 and 4 nines, we've got 2.0003. 0 and 3 nines, or 4 nines, we've got 0.99988. Let's call that a 9. 0.9, well, okay, we'll leave it in there. 0.99988. 0.8 and 3 nines, we've got 0.89981. 0.7 and 3 nines, we got 0.79977. 0.6 and 3 nines, we've got 0.69974. 0.5 and 3 nines, we got 0.59973. 0.4 and 3 nines, we've got 0.49976. 0.3 and 3 nines, we've got 0.39981. 0.2 and 3 nines, we've got 0.29988. As well make that a 9, but 0.1 and 3 nines, 0.1 and 3 nines with a 3, so 0.0 and 3 nines, we've got 99.9 millivolts. We've changed our range, so let's go ahead and we'll keep that, but I'm going to reduce my number of digits to 4. Just makes it easier on me. All right, so we've got 99.9 millivolts dialed in and 99.9 showing. 89.9 dialed in. 89 point, I'm going to call it 9. 79.9 dialed in. 79.89 should be 79.9. We've got dialed in. We've got 8, 9 coming out. 69.9 dialed in, we got 69.89. 59.9 dialed in, we got 59.89. 49.9 dialed in, you got 49.89. 39.9 dialed in, you got 39.9 on the meter. 29.9 dialed in, you got 29.9 on the meter. 19.9 dialed in, you got 19.91. You got 9.9 dialed in, you got 9.91 or 2. 8.9 dialed in, you got 8.91. 7.9 dialed in, you got 7.91. 6.9 dialed in, you got 6.91. 5.9 dialed in, you got 5.90. 4.9 dialed in, you got 4.90. 3.9 dialed in, you got 3.89. 2.9 dialed in, you got 2.92. 1.9 dialed in, you got 1.94. Then you got 0.9 dialed in, you got 0.91. 0.8 dialed in, you got 0.80. 0.7 dialed in, you got 0.70. 0.6 dialed in, you got 0.60. 0.5 dialed in, you got 0.49. 0.4 dialed in, you got 0.38. 0.3 dialed in, you got 0.16. Now I think what's happening here is my meter is failing us. It can't read this low. So if I go to 0.2 dialed in, we get, yeah, it's definitely what it is. If I go back up to 0.4, we get a reading. 0.38 at 0.4, that's our lowest reading. If I was to add 1 to it, so we got 1.44, let's see, this is 1.4 on the dials over here. 1.4. If I go to 3, we now are able to read the 3. We got 1.3, 1.2, 1.1, 1.0. There's no problem with the decade. It's functioning. The meter just wasn't able to read the voltage without that extra millivolt added to it. I can't read anything under 0.4 millivolts. There's 0.4. But remarkably, we were able to divide a AC voltage very precisely down to like a millivolt or better, actually to a fraction of a millivolt. So very few ways to easily do this. This is one, definitely. Along with it, I'm going to provide a CD that has a lot of information on ratio transformers, including this one. And it'll give you a lot of information about how to use it, how they're made, how precise they are, and so on. Okay, so I promised that I would provide the results of the performance test. And I'm hoping that we can see this okay on the screen. What we have here, this was taken May 11th, 2020. Here in blue are the voltages selected via the dials on the front panel of the ratio transformer. And then next to it is the voltage that we obtained, measured with my HP 34401. And the only liberty we've taken with the data at all is that we limited ourselves to the same number of decimal places as is available on the front of the ratio transformer dial-wise, and we rounded anything that was below that to the nearest rounding point. So if it was less than 0.5, then it went down. If it was above 0.5, it went up. And the results are displayed here. And then what you see in the red down below, these are the actual percent errors. I'm not talking about an error expressed as a percentage. I'm saying this is the percent error. So you're seeing here 0.001%, 0.007%, 0.013, 0.019, so on. And when you get down to the lower numbers, like we get down into the decade here where we switched to millivolts because my range on the HP changed. Again, we restricted ourselves to the number of to the decimal place that we had available to us. 0.9 was the 0.9 millivolts is the smallest decimal place using 10 volts that we had. So as you can see, the results are pretty remarkable. I mean, basically, with that rounding and with the restriction to the number of digits we had dial-wise, we, for half of the numbers checked, we got 0% error. I mean, this is amazing. These little transformers do an amazing job at dividing down AC voltages as long as you remain within the voltage times frequency range that's expressed on the front of the meter. You don't overload the transformer, burn it out or whatever. It does a remarkable job. And these test results, they'll be provided with the meter, along with a lot of data on the CD, like I said, regarding the Gertsch line of products. And outside of that, thank you and happy bidding.